So I probably should have put ISIS on the slide as well. So ICD is the ISIS computing division. And one of my sort of side roles within this is being part of the sustainability working group there. So it's been really great to hear sustainability mentioned in quite a few talks already and see some calculations. And I'm grateful to have an opportunity to go into it a bit deeper. So these are two things that really interest me. I'm not an expert in everything I mention in this, and I've probably missed some things, so tell me at the end. So the first off is, why is this important? Why do we want to do this? So things are already pretty bad and getting worse. So we've, in the past few years, passed some big milestones. So degree of warming, we've passed the 400 parts per million threshold. We can't stop this. We're now deciding how much worse it gets. So these are various trend lines based on different predictions of what we might do. In some ways, we're getting into a better position. So there's now net zero policies from our governments, from our funding agencies, and all through our organisations. So we have quite a push to actually do something. Computing, it's not the biggest CO2 source in the world, but definitely within research, it's significant and growing. And there's a quote from the UN Secretary-General there that's quite strongly worded. Oh, another thing, I've put quite a lot of links in my talk, so go away and read as many as you can. So in terms of UK research, we have a range of big carbon heavy things, and some of them are our large compute facilities, and then also our accelerators, and then a few other things as well. And I'm a software engineer, so there's a sort of question of, is this a software problem or a hardware problem? And I think it's a bit of both. So there's the term software sustainability gets used in two completely different contexts. Most of the time you hear it, they're talking about, will this software project be useful in the future? Is it maintainable? Is it documented? Does the license allow me to keep using it or allow other people to come and use it? But there's a kind of, you can step back and say, am I sustainable in a larger societal context? And this is more like, will anyone want to run my software in 20 years' time? You know, will we still be doing big science? Will we still, or will we've decided that you know, giant data centers are just use too much energy? So there's this Karlskrona Manifesto is quite an interesting document that talks about some of the things we should be thinking about. So climate is just one part of sustainability. So if you know the UN sustainability goals, they cover a wide range of things. I think it's really important because it actually interacts with all those other things as well. So health and housing and everything. In computing, we often think about our use in electricity. It's really easy to measure. So this is just like a cheap watt meter that you can buy and plug all your devices at home in. If anyone has a UK plug and wants to try anything, then come find me. But you can get similar devices, industrial devices, if you want to measure. And we all get a bill which says our usage at the end of the month. So, you know, something we can be aware of. But even so, it's still complicated. There's still a lot to think about. So I try to list a few things that are sort of the carbon footprint of a software engineer. And some of them are kind of generic. Anyone who works in the office has those requirements. Some of them are quite specific. They're also, within carbon accounting, there's these idea of scopes. And you know, is this a scope 1 emission or scope 2 emission? But I think it's also useful to think about what influence you have. So where your software, how your users run your software might not technically be within your carbon accounting, but it's something that you do have influence on, and can have an effect there. And you know, you can go outside of your work and talk about your food and your house and lifestyle things as well. So there's lots of areas to think about here. So this is kind of going, it's not just all about electricity, even though that's the easy bit that we can get a good handle on. So these are some product lifetime carbon footprints, which Dell produce for, I think, pretty much all of their hardware now. And one of the things I found really interesting is the difference between kind of the consumer end of hardware and the server end of hardware. So for a laptop, 80% of its carbon footprints, this is assuming a 4-year lifetime, is its manufacture. So the kind of things of we should send less emails because emails have a carbon footprint. Actually, how you use your laptop doesn't make so much difference once you've bought it. The best thing you could do would be to make it last 6 years instead of 4. With servers, it tends to be the other way around, and part of this is because you need cooling. So for each watt you put into a server room, you need to extract that with your cooling system. So you can find these for most of Dell hardware and also from a few other manufacturers. One thing to note is that these seem to be for the base configurations. So I recently was reading this thing at the bottom, that SSDs actually have a huge manufacturing carbon footprint because they have many, many layers of silicon layered on top. So they have a lot more silicon than you'd imagine. So some good news, making computers more efficient is actually something that we've all cared about for a long time. So I think we all know that good algorithms, good data structures makes your software faster, and that is a big part of making it more efficient. There's other things to think about, so good languages or using well-optimized libraries, and following the discussion a few days ago, I've got another slide on that. But also, a lot of it comes down to avoiding unneeded work. So can you cache your data? Do you really need to invert a matrix because the paper you were building your software based on says invert the matrix and do this, or is there a more efficient method to do? Do you need to sort your list if you only want to find the largest item? What can you take out of loops? Where can you remove I/O? And compression is something that was mentioned a few days ago. What can you save by compressing some of this data? So yeah, should we stop using Python? So there's, I think some of you will have I think some of you have seen a table like this or something similar. I've cut out the middle because there's a lot of languages. I think Fortran would be near the top of that. I'm surprised it's not in with the others, but I guess it's just the particular test that's in this first reference here. So there's obviously some limitations with that paper. They took a single algorithm and wrote it in a fairly similar way in each of the languages. And you don't have to use Python for very long to realize that you really shouldn't be using loops for doing numeric calculations, because those are slow in Python because of how it's interpreted. But it's actually not that hard to make Python a lot faster than it normally is. And this second paper, which this plot is from, actually shows that going from a fairly naive implementation to starting using some of these tools that do various bits of compilation on Python code, you can actually beat a naive C or Fortran implementation without a huge amount of work. So I recommend that second paper. But I think a key message is don't use raw, naive Python for implementing your algorithms, because that really is slow. The other thing is there's this 80-20 rule, or sometimes the ratio is even more than that. And it's the same as when you're optimizing code. Most of your time of your software is spent in a very small region of code. So that's probably the bit that you want to maybe rewrite in a compiled language. So I asked around our group at ISIS, and we found a few examples of things that people have been doing. Some of this they were doing anyway. Some of this was kind of inspired for sustainability. But some of them, and some of them are fairly small things, but it's interesting to start thinking of this from a sustainable point of view. So there was an issue, or the way the managed release notes were done was that everyone would make a change and update this one file, which meant everyone's pull requests would conflict and keep conflicting, which meant the continuous integration and testing kept on running, and then you'd make a change, then someone else would do it. So there was this plan to move them into one file per change and then just concatenate them when you do the release. I'll jump ahead. Another interesting one is this, which was actually using software to choose the experimental setup parameters. And this means you're doing a bit of work on a computer, but in this case, there was a saving in beam time, so that it was able to get the same data quality out by tweaking some of the experimental setup for reflectometry, I think it was. So I think that's a good example of, yeah, sometimes it's actually good for your computing to use more energy and do more with computers, because you can be taking away something that is as we saw in those plots previously, running an accelerator takes a huge amount of energy. So a bit of computing to save some of that is a good thing. So then these are sort of some broader things that are maybe just ideas, but maybe these might get someone thinking. So the carbon intensity of the electricity that comes out of your wall varies a huge amount by time and place. So this is at the top a plot of a week in March, I think it was, for the UK energy grid. And you can see that it varies by a factor of 3 by time of day and time of week. And below with the colours, you might be able to guess what some of those are. That's 24 hours of the energy sources for the UK. And then you can also, from this electricitymap.org site, you can see maps of the whole of Europe. So that's the carbon intensity averaged over last year. And you can see there's a big difference depending on what energy sources or what electricity generation is being used in the country. So yeah, this is the question of, are there tasks that don't need to be done immediately that could be maybe moved to a different time of day that might be better? And again, this is pushing towards the edge of my knowledge, but questions around infrastructure. So we often have lots of users who have lots of tasks to do. How many computers, what resources do you actually need to do that? Do you provide more resources so that there's always something available and someone can get things immediately, or do you make people wait in a queue? Do you need 5 nines of uptime for a particular task? Is that important? Could you have less redundancy? I think we'll always ask for the most reliable thing that's on offer, but sometimes that can have a big energy cost in terms of machines. And this is a kind of just a mock-up at the bottom, that if your users were given, when they submitted a job, something like this, which maybe gave them an estimate of, you can do your job in 4 hours and you will use this much CO2. Do you want to click the eco mode and I'll run it slightly differently and it will use less CO2? I think I'd click it because 4 hours and 12 hours is both overnight. So if you start a job in the evening, it doesn't matter really when it runs. But obviously it depends a lot on the user and what's happening. So I think finding ways to estimate carbon and communicate that well with users could be really important. And so I wanted to say another thing. So some of us have travelled quite a long way. Plenty of people have travelled further than me, but Manchester is about 1,000 kilometres away, which is a nice round number. So I decided to travel not by flying, and took a rather long journey with a train and a night bus. Night bus is a lot cheaper than the train, so it meant I could stay below the cost of flying. And there was a ferry involved as well. So I did another table of calculations. And so you can see the various distances for each of the modes of travel and how much they contributed. So it can make quite a significant difference. And I think that was a similar number to what you had for flying to a facility. This is using the UK government average values, which is, with all these things, there's how much depth do you really want to go into it. So these are just averaged based on distance. And you can see interesting things like the carbon per kilometre for a train in England is very different from a train in France. And that's because we still have quite a lot of diesel trains. But the train I was on from Manchester to London was an electric train, so that figure is probably an overestimate. And yeah, if anyone is usually travels by flying and wants to maybe take a train to the next journey, I really recommend this website at the top. It has loads of information about rail travel in Europe from a train nerd who has, I think, taken all the trains possible. Seat 61 was his favourite seat on a particular train. Other advice: train is nicer than the bus, but more expensive. So that's something you have to weigh up. If you have time and you're changing the stations, walk outside. There's some really nice stations around Europe, and there's coffee shops outside. Some bonuses like no sleeve restrictions at the airport, so you can take water and wine and everything else. Check your time for changes, because I once booked something for a university travel, and the person actually booking the tickets thought I could get from Gare du Nord to Gare de Lyon in 30 minutes, which is not true. I managed to stop it before it was booked. So yeah, as a summary, this is a huge topic. There's so much, you could do a whole conference on it, but there's really big impacts, and I think there's, if we're all thinking about it all the time, then we can probably make some changes that will have those big impacts. Good software reduces energy consumption, and it ties in with, it's very well aligned with what we all think of as good software. So it's not doing something completely new, it's just optimizing for a slightly different set of parameters. Things to think about is, does it need to run? Does it need to run now? What resources does this need? And does it really need these resources? Have I just asked for 64 gigabytes of RAM because that's a round number and it was in the menu? Or could I work with less? Where can you have influence? So if your group or institution has a sustainability team, try and join it, try and listen in. If it doesn't, just create one. Just say, this is the sustainability team, and find 3 people, and then you can start something. And given that everywhere has now net zero policies, this is a good way to form a little group, talk to management, and make some changes. So I just was going to put some more further reading there, but yeah, download my slides and click all the links, please. Thank you.
Very much, Sam. We have a coffee break coming up, so we can defer most of the discussions there. But do we have any burning questions? Jerome, go ahead.
Yeah, right. Maybe there are some physicists or chemists in the audience who have been surprised by the difference of figures that we get as a CO2 emission for oil, natural gas, and biogas. Well, if biogas is recycling vegetables, the value should be 0. And I don't understand why biogas is half normal gas, while it should be either 0, either the same numerical value as gas, because technically speaking, it's the same. And the difference between gas and oil, I don't understand either.
I think this is because it's these are considered the whole life cycle. So your biogas has to be collected from either farmed specifically or collected from waste material, and there's that whole industry to actually convert something into something that you can burn. I guess the difference between the different carbon sources is because of the ratios of carbon to hydrogen.
Hydrogen weighs nothing.
This is grams of CO2 per kilowatt of electricity you get. So when you burn gas, some of those kilowatts of energy are coming from the hydrogen, which then isn't producing carbon dioxide. Whereas coal, everything is carbon.
Could also include the transport of the fuel and things like
that.
Yeah.
Those numbers are from the IPCC, so there'll be an incredible amount of detail of where they came from.
Okay, thank you, Sam.
Thank you.